so you know, if you ask a question, you may be recorded.
Yes, sir.
Okay, so before we wrap up our three body diagrams, I want to have a little demonstration on Newton's third law. Okay? Right about its first law, second law, third law. Okay, let's see if I can have someone up here. Yes, Hensley and Shelby, come on up here. Okay. All right. So get right there. We can all see what's going on.
Hey,
here.
Matthew.
All right. So, all right. Hensley, push Shelby. Push her. Shelby, stop pushing Hensley. Okay. Hensley again, please. Shelby, stop pushing Hensley.
I know what he's saying. I get it.
What am I saying, Anton?
Because she has like
Force
two, and so like she's stopping Hensley from that motion.
Okay. All right, now Shelby, go ahead and push Hensley. Hey, Shelby, stop pushing on Hensley. How many times are you gonna push on Hensley all this whole time? Okay. All right. Newton's third law says that forces come in pairs. Okay. There's always a pair. Okay. There's always a match. Every force is part of an action and reaction force. Shelby, well, in this case, Hensley pushes on Shelby. Okay. But guess what Shelby's doing right at that very moment? Pushing back. If she didn't push back, then
She would fly.
there'd be all kinds of weird stuff going on. We'll talk in a second.
What would happen if I did?
What would happen if you did not push back? Well,
I would push you over
if
and just go.
you would just, it would be like a frictionless surface where you would just slide on. But what happens is your feet kind of have some friction, and you're kind of using that to lean yourself forward. Otherwise, if there was no friction at all, you would just.
Like push me.
Yeah, there you go. Causes it was a force, and it would cause acceleration. Okay. All right, thanks. Take a seat. You did a good job there. Okay. Another example. Okay. Lay your hand on the desk. Okay. Your hand is exerting a force on the desk. Yes. Okay. Lay your hand on your head. Now, Simon did not say lay your hand on your head, so you're all busted.
Okay.
Sorry.
Oh my God.
Wow.
Wow.
Anyway, all right. Now, seriously though, your hand is exerting a force on the desk. If it's just laying there, okay, just laying there, okay. What is the direction of the force of your hand on the desk?
Down.
Down. What is the direction of the force of the desk on your hand? Up. And in this case, they are equal and opposite. Okay? What if one of them was stronger than the other?
Boom.
The table would break through.
Okay. I need somebody who can get hopping mad. Jesus, come on up here. Hopping mad. All right? All right? All right, you're going to ask the question, Mission. Okay?
His ears will get big.
All right. I want you to exert a force on the earth.
You already are.
He already is. Okay? I want you to exert so much force on the earth that you accelerate in the upward direction.
Oh my gosh. That vertical.
There we go. All right. Good job. Now, wait a second. Okay. Now, he exerted a force on the earth, but at the same time, what happened?
The earth exerted a force
On him. Okay. So that's why he went up. All right. He and the earth exerted a force on each other. All right. And what happened to Jesus? He went up. You'd laugh, but it did. It really.
Wait, what is
really
that?
We were all jumping at the same time and then like.
And the earth.
We would probably just fly into the sun.
All right. You take a seat. Jesus here. Thank you. All right.
Just instantly.
Let's throw a number here. Okay.
7.
17.
His mass is 70 kilograms. Okay. So the mass of Jesus, okay, is 70 kilograms. Okay. How much do we think that he accelerated upwards?
2. 71.
About 3 feet in a second.
My boy.
that would be about 1 meter per second, maybe about
Half.
0.2 meters per second. The acceleration of Jesus was 0.2 meters per second squared. All right, grab a calculator. What is the force that he exerted on the earth in this imaginary situation? Also, trig chart. Who's got third out trick chart? Calculus chart. Someone with a smartphone or MacBook.
I got you.
Look up mass of
That's
the
so
earth.
smart.
Look up the
She already
mass
did that.
of the earth.
Siri, what is the mass?
What is the math?
5.9721986 times 10 to the 24th
She is correct.
I
can't
Kilograms. Okay.
The mass of the
All
earth?
Right, now watch
That's
this.
the mass of the earth?
What was the
No.
force that Jesus
What do you mean?
exerted on the earth?
A lot.
14. I mean, well, hold on. Let's just do the math here. Force is mass times acceleration. So 70 kilograms
The ears
times
cause drag, though.
0.2 meters per second squared. So
Cause air resistance.
14 newtons. Okay? So he exerted 14 newtons on the earth. Okay? And also at the same time, the earth exerted 14 newtons on him. That's why he accelerated. Okay? So because this is the force of, J, or actually technically since it is this mass and he accelerated that much, this is the force of the earth on J. We have said that that is exactly the same as the force that Jesus exerts on the earth. 14 newtons. So therefore, hey, we've got a mass, we've got a force, there is an acceleration of the earth, okay? Acceleration is the force divided by the mass. So that would be 14 newtons divided by 5.97 times 10 to the 24. You can also hit that E button right there. So 5.97 times 10 to the 24. I need someone with the number, somebody else to verify it.
I totally put that on wrong. That was embarrassing. You didn't see that.
Okay. I did not see it. So
5.94.
E.
5.94 times 10 to the,
I got 2
2.4, yeah.
Yeah, I got 3 numbers.
5.
okay.
Times e
2.34.
times e to the 24.
So you wouldn't say times e to the
Well,
24.
times 10 to the 24.
Times 10 to the 20. Is it positive or negative?
Negative. Yeah,
Okay.
negative.
Okay. It's a good thing that's negative.
Because then.
Because what that really means is, move this decimal 24 times that way. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And then that extra one is 24. So 2, 4
Dang, Jesus.
meters per second squared. Good job, Jesus.
You're so heavy.
Did the earth actually accelerate?
Yes.
Yep. That much downward.
So does that mean that we're people
No.
jumping at the same time?
No,
We're
Jesus,
moving
why'd
it
you
up?
do that?
But does it ever come
Could,
back up?
if enough people jumped at the same time, could they move the earth? Well, if one person jumps, he's moving the earth.
No, but like,
But wait.
at least.
Could we
Bigger amounts.
could we adjust the orbit of the earth?
Yes.
No.
Nothing.
Is
Okay.
the gravity?
Anton, I saw your hand next.
Ooh. Okay, so like, does the earth come back up or just stay at that position that it's at now?
Ooh, that's another great question. Okay, because once they're separated, then there is gravitational force of attraction between them. So yeah, just come right back.
So here's the earth, and we got
You're making
like
it.
people who stand all around it. You know how it's like a
The earth is
circle?
flat.
Right? It is a circle.
It's like a circle.
Yeah.
So if we got
Alright.
everyone that like around it, and we all jumped at the same time, and like we landed, but would it go like this?
we would crush the Earth.
That's more of an issue of like the substance and like the way that it is, and dirt is really, you can compact it, and then there's and frankly all the weight of just all of the people like all combined in the whole Earth is nothing
We got all
compared
the
to just like
animals to do it too.
doesn't matter. I don't think you all
That's why
realize
you're
okay,
here.
if all the
Look,
people
it just changed to 2-5.
if all the people in all the world just like were all of a sudden to die and we were to pile all of their bodies up, it would be like this much. Okay, I mean that's really. I mean the Earth is huge.
She's not
I'm
wrong.
not think you really understand how thick the Earth is.
Ooh.
How much mass there is.
Okay.
What if it is really, really dense in the middle too?
No.
Okay, like
She's thick.
crazy dense. Okay, so no.
Journey to the
can't-
center of the Earth.
No,
Will
no.
we ever achieve going to
What would happen?
I do not know the answer to that question.
Okay.
Okay.
Other question? before we move
Using
on?
physics, what do you think would happen if we actually like drilled a hole to the center of the Earth?
It would vent and we would die.
Like, wouldn't it like?
There'd be a lot of pressure and stuff like that. I don't know, but that's you're kind of at the edge of my knowledge when it comes to drilling down the Earth because
There's an edge.
The Earth would get triggered
Everybody
and
jump at the
it would
same
die.
time?
everybody jumps at the same time.
Oh,
Everybody's
that's what
somewhat
we've been
semi-distributed, and therefore now if everybody's in the same area and were to jump. You could get a whole lot better of a situation if you had basically like a bunch of really strong rockets or something that were taking off at the same point. Or better yet, even like getting those rockets and flipping them around upside down so that they're like pushing, you know, the Earth
That's possible.
like in this direction, okay? They had to do that.
We could just move the Earth so we're not swallowed
yes.
by the sun.
The robots did that in Futurama season 3, I think, because there was some problems with the global warming and stuff. So they kicked it out.
But I want to.
So they actually kicked the Earth farther out away from the sun because it was getting too hot. So they kicked it this way, and then what happened is then a year was a week longer, and so they called that Robot Week, and all the robots got to party for a week.
That's pretty weird.
Yes.
So, using those laws, can we find out the force if like 100 people kind of?
Yeah, 100 people, something like that. But that's not a whole lot of. We could figure out their mass and their acceleration. This would scale up. Okay. What's really fun though is if you ever played the game Super Mario Galaxy, if you were to be on like an asteroid or something, okay, and you were to jump up, then that would really be measurable. Next chapter, when we learn about gravity, there's some of them that if you were to run and jump, you could actually put yourself in orbit around.
No.
You know how lit that would be? We could just go anywhere.
Or if you get high enough and then just jump, then you can put yourself in orbit.
Gabby's done.
You know, I never could get Mario into orbit, and it's probably a good thing because then he just wouldn't come down. So, but it's a really fun game if you ever played it. You do some physics stuff with gravitational fields. You should play it. It's a great game.
Like the
All right.
physics.
I'll bring a Wii and then we just.
I got a Wii. Let's go.
Okay.
I have the first gen.
I sold mine.
Has the first gen Xbox.
Oh golly.
All right. Two volunteers have come up here. Celine and Cameron, come on up
That
here.
was
That was great.
great volunteering, guys.
Yes. Take one for the team.
4 girls here.
Who that? Same phone. Who this?
Okay. I have here 2 force sensors.
Same
All right.
Pop.
Now we need to be able to see this, and I need the screen to be able to see this.
Yes.
Okay,
Yeah,
so,
basically.
It's kind of glaring.
okay. We have a little bit of glare. Gabby, hit that light there for us,
Hit that.
Hit it.
please. Thank you.
Our girl.
All right.
That's better.
Kimmy, go ahead and put some different forces on that force sensor so we can figure out which one's yours. Don't do anything.
She's not.
All right, so is that yours? Okay, all right, that's yours. All right, now I'm gonna need help from you ladies right here. Hit the record button, Josie, so we can, that's this button right there. Now,
You can't put it in.
all right, so we're recording, go ahead and do some force action there. There we go. All right, we can see that she's got positive and negative force, looks good. All right, same thing with you ladies over here. Hit that play button here, and Celine hit some force. Oh, she's making a nice sinusoidal curve. Now hold it out. Hold out. Just hold it there. Hold it out. Okay. Great. All right. Now here's what we're gonna do. connect them.
Oh.
Connect this to that. I know. Okay. Ladies, how about y'all stand right here? We're gonna need the, okay, that's good. Alright, now, what they're gonna do is go back to just regular reading mode so we can just, that's the graph indicator up there at the top. There's also a stylus. Alright? I'm gonna see if I can, is there a really bad glare still? Yeah, right there. Alright, ladies, go ahead, pull back and forth on those force sensors. Let's see what happens.
No.
Now, as Celine pulls on hers, okay, look what happens to Cammy's. So Celine pulls hers out, okay, then Cammy's gets pulled out. Okay, as Cammy pulls hers, then Celine. It goes back and forth. And look, do you see them tracking?
It's almost even.
It should be, because if you pull with 5 newtons this way, this one device here is going to be, hey, I just got pulled out 5 newtons. You see what I'm saying? In fact, if we graph it, all right, how good are you two at synchronizing?
Freaking great.
All right, here we go. You're going to hit the record button in 3, 2, 1, go.
Oh, no.
There was a...
Just keep going, just keep going, just go. We should...
Oh.
Oh.
Oh. Hey.
Oh.
Oh, dang. That was actually really good.
Pretty cool, huh?
Yes.
Kidding? I'm totally kidding.
So, all right. Let's see if I can do it from my screen. Think I can do it from my screen? Go.
Sorry.
Whoa. All right. Thank you, ladies. Take a seat. I'll take those 4 sensors.
Wow.
All right. So, what they've just done is they've just demonstrated for us Newton's third law. That is, this one was pulling out maybe with 2 newtons or whatever. Then this one also felt being pulled by 2 newtons. Okay. And if we could adjust this so that one would be positive, one would be negative, but I think we get the idea. Are you convinced of Newton's third law now?
No.
Yes.
No? Well, too bad, because we're pretty much...
That's all he's got.
Yeah. I don't have any other tricks in the book. So if we look over here right above Gabrielle's head, we can see the 3 Newton's laws.
Please don't.
First law, an object at rest tends to stay at rest, an object in motion tends to stay in motion. What's the second law? Anybody?
Direction of acceleration is equal to direction of
Yep, that's
Force.
the fundamental idea is the acceleration F equals ma, or A equals F over m. And then the third law, every force is part of an action-reaction pair. All right, every force that you have, it exerts there's another force that's counteracting it. There's a picture there, if you can imagine this. You're like, oh, I don't know. What if you had a hammer and a nail? Okay, so a little thought experiment. Let's say you've got a nail right here, and then you have a hammer. Okay, there's a hammer there. All right, when the hammer hits the nail, okay, at that moment, what does our object is the nail? The nail feels a force downward on it. Would y'all agree with that?
Yes.
Okay. Now, this is where students sometimes make a mistake. They say, oh yeah, and the nail also exerts a force back up on the hammer. And so they draw their free body diagram like that. And that is not correct, okay? Because you remember, every force has to have an object. And that's the thing that's acting on, okay? The force of the nail on the hammer is acting on the hammer, okay? So the up arrow, okay, would go, the colors here, when I circle the hammer and I draw its free body diagram, so this is of the hammer, and I would draw that arrow upward. I should make it actually equal and opposite, because I'm running out of room here. So this right here is the nail. So some students say, oh great, after we talk about Newton's third law, they say, do we have to draw like a whole bunch more arrows all over the free body diagram? And the answer is no, okay? If you have a ball and it is exerting a force, weight is pulling it down, okay? And gravity, and the ground itself is pushing it up, okay? But you could say, and that's the normal force, but we're not gonna draw any more forces, because like, oh, and the ground is pushing up, and this is pushing on the ground, all that other stuff like that. We're not gonna draw anything that's acting on the ground. Does that make sense? We're just talking about what's going on with the ball. That's why we always circle the object. Okay? Alright, let's go ahead and get out that free body diagram chart. We're going to do a few more of those, and then we are going to be finished with chapter 4.
Hey. 10.
Let's see, where did we stop? Do we do the ball? Let's do the wrecking ball. You do the wrecking ball one? You're welcome. So, allow that. A wrecking ball, no need for acting out anything.
It looks like a really long arm holding a gun.
Alright, well, it's smashing that 3-story building from earlier.
Is that another hand?
It's a giant.
That's
It's
a
a toe.
hand holding it. Okay? The hand is holding the ball.
It is not a hand.
What is going on with that wrecking ball? Let's just focus on the wrecking ball. I picture it a lot better with the wrecking.
Tension.
There is tension.
Wait.
There is weight.
There is.
The ball is swinging in this motion, but does that matter?
No.
No. Now, just to be clear, tension is a vector because of the force. Weight is a vector, okay? Velocity is a vector, which means it has a magnitude and direction, but it is not a force, okay? So just make sure you understand the difference between those things. So, if we were to draw this, the free body diagram, we would say tension is probably along some sort of diagonal like that, and weight is way down.
Why is tension going the other way?
Like swing.
It's because, as far as what this ball is concerned, the rope is the cable is pulling it this way.
Oh,
If it was pushing it that way, then it would.
Yeah.
That's good enough for us because we don't have any other angles. I want to get something
You should
that
do
has.
the one with the hand foot claw.
Yeah, I was not pleased with that
Lucky
one.
Finn.
I don't feel like we really need to do any of that. This, yeah, that's a foot there.
It looks like a boot from SpongeBob.
Yes, there you go.
Yeah, that one.
Here we go. This is a good one. This is 34. A skier being towed up a snow-covered hill by a tow rope.
That's a good.
The hill has a 45-degree incline. I also like that picture better. Okay?
Normal.
There is a normal force.
Same thing.
There's weight. It's actually a wire there. So yeah, so there is tension. There wouldn't be too much friction, but there's some friction. Kinetic friction since he's sliding across the snow.
Is there no? There's no drag.
No drag. We're gonna go drag. Okay. Now, do not draw this picture yet that I'm gonna draw right here. Okay. I want to show you how this gets really messy. Okay. So, here is the person. What's the direction of weight?
Down.
Down. Okay. What's the direction of tension?
I mean, well,
Yeah, it's gonna be along that 45. Okay. What's the direction of the normal?
this way.
Normal, by definition, Old English definition is always perpendicular to the surface, okay? So that's out like that, okay?
Wait, perpendicular to the surface?
Perpendicular to the surface, and the surface
How's that perpendicular?
is like that,
Oh, I see it, okay,
okay?
the thing slanted.
And then friction is opposite of the direction that he's moving,
So.
So it's going opposite.
so it's gonna go like that, okay? So like, so don't draw this yet. Now, you look at this, and this is yuck, right? Because here's our y-axis, and here's our x-axis. And out of those four forces, only one of them is actually lined up with the x and y axis. Do you see that? And I'm gonna have to turn this into an x and y part, this into an x and a y part, this down here into an x and y part. Do you see what I'm talking about? Is just, it's ugly, and we don't like it. However, Crystal has a suggestion.
Good job.
Crystal, why don't we tilt the axis? Okay, we have that, we are like gods in this physics universe with this sphere problem. We are controlling everything. Let's just say that's the x, okay? And that's the y.
That's a nice dance.
Alright, thank you. So, let's say, boom,
Hit that actually.
that's the x-axis, and that's the y-axis.
Can we draw this down?
We will draw this now. So that's our x and y axes. So, hey, this is really helpful. Look, tension, right along the x-axis. Normal, exactly perpendicular.
Wow.
Kinetic friction, exactly along the x-axis, but in the negative direction. And then there's weight. Okay? Now, we're going to have to deal a little bit with weight, but that's okay.
I still love it.
So, yes, question.
Why does it matter if all those others have to be on the axis and not?
Why does it matter? Okay, great question. You have me the lights for just 1 second. Because here in a minute, we're going to write Newton's second law. Summation of forces in the x direction equals blah plus blah plus blah plus blah. And then we're going to write summation of forces in the y direction equals blah plus blah plus blah plus blah. We're going to add them all up so that we can actually, in chapter 5, do some analysis, figure out what the acceleration is and what the mass, well, we know what the mass is, but. So we want everything lined up along the x and y axis, so we can just add all the x's up and add all the y's up and find something. Okay? Great question. Gabby, hit those lights again. The problem is we're going to have to break this weight down, and we're going to do this one time and just do a very small amount of trig, but once we do it once, then you'll have it set forever. Okay? So weight is going straight down, okay, in this world, and the horizontal is, well, horizontal to that. We are told that the angle between the horizontal and the slope, in this case, is 45 degrees. I'm going to change that, though, because 45 degrees is exactly in half of 50, and it ends up being 45 everywhere. So I'm going to change it just to 50 degrees. So that way you don't assume that it just gets repeated everywhere. So that angle right there between the horizontal and the diagonal is this angle right here, 50 degrees. So now we play the geometry game. What is this angle right here between the dotted line and the red? 40. Okay, because notice for this, that's the x-axis and the y-axis together, that forms 90. Okay? Then we can go down over here. This angle right here, we got to figure out which ones are these. Well, this blue line and that dashed black line are 90, so that's, or 90 together, that's 40, so that puts a 50 right there. Okay, and then there's 40 again, yeah. Let's see, I'm going to try to, so here's what we're going to do though. I'm just going to use that 50 though for right here, and it's a little bit weird, but I'm going to draw the part of the weight which is on the y-axis right here. So this is WY, and the part of the weight which is on the x-axis, I could draw it right here, so down and over, but I'm actually going to draw it over here. So just so you know, it's the same thing. This part is the weight along the x-axis. Okay, so it's I'm going to draw it along the x-axis there, but it's the same length as this part right here. And then we're just going to do a little bit of trig. Okay? So if I've got 50 and the triangle looks like this, if I just draw it separately. W, WY, WX, and 50. So if I want to find WX, and I've got the 50 right there, and I know the W, what trig ratio might I use to kind of set that up? It's opposite of what you might think. It's the sine. We would say the sine of 50 equals opposite WX over W. So therefore, multiply both sides by W. WX equals W times the sine of 50. In the same way, looking at WY, I would say the cosine of 50 is WY over W. Okay? Give a little space there. Pull the elbow room is always good. Multiply both sides by W. So we've got W cosine 50 equals WY. Alright, so we'll circle that. And we'll circle that. Gabriel, leave those lights one more time. So my modified picture, you don't need to draw it, but it looks like you've got normal force there. We have tension going up the line. We have the friction force right there. We also have along that line the weight in the x direction, okay? Or I'm going to just write it as W cosine theta, and down here we have W sine theta. Is that right?
Yeah.
No. The other way around. In the x direction it was sine. W cosine theta. That sometimes throws students for a loop because they're like, I finally got this. The sine deals with the y over the r and the cosine deals with the x over r. That's true, except in ramp problems, because this angle is, if y'all notice it, if you're on a pre-calc class, is that the reference angle?
No. Well.
No, it's not the reference angle because it's between there and the y-axis, not the x-axis. That's why you can't just do your little magnitude of the hypotenuse, cosine, magnitude of the hypotenuse, sine for the x and for the y. Alright, if you don't know what I'm talking about, don't worry. So, let's write Newton's second law here. So the summation of forces in the x direction. Everything that's to the right is positive. So, tension. Everything that's to the left is negative. So, minus kinetic friction force minus weight. I'm just going to put sine theta equals mass times acceleration in the x direction. Newton's second law in the y direction, everything that's up, so is positive, so normal. Everything that's down is negative, so minus W cosine theta equals mass times acceleration in the y direction. You're like, great, why am I writing these equations? What am I going to do with it? And the answer is just wait. Chapter 5, we will do lots of fun things with these formulas, but you have to know how to write them first. And students, every year, they get to the part where they're writing the formulas and then they're trying to solve it, and there's just so many parts of it that research has shown students learn physics best if you can just get them to writing this and getting real comfortable along that way, and then you can start doing some cool stuff. All right. Does anybody have a question about the trig that we did there? Yes. Here, go ahead.
So every time it's not the reference angle, it's gonna be the opposite.
Yeah, but I would just draw the triangle just to be sure. I can tell you this, every time that they give you this angle right here, okay, then the part of that weight which is along the y-axis is W cosine theta. And every part that's along the x-axis is W sine theta. That's gonna work no matter what. Yes?
So wait, sorry, I'm actually gonna ask. So when you're doing cosine 50 equals, you know, I believe that's WY over
Mhm.
W, you're looking for the other angle? Like, that's not mentioned?
Right, well, we're not really, the thing is I'm normally gonna give you the weight, okay? And so that number is normally gonna be known, and that theta is normally gonna be known.
Right, but you're looking for an angle or just an amount? I'm confused. If you're looking for the other angle.
I'm not looking for any other angles.
Okay, that's what I was wondering.
What this is solving for the length of that side.
Oh, okay, cause I was like, why don't you just, you know,
That-
50 plus 90?
Yes, exactly, that angle is 40, yes. But what I'm interested in is what is that side length right there?
Okay.
So, great question. Let's do another one that's similar to this, but maybe just, we have another one. Okay, sure, here we go. Car's going downhill, very last problem, 33. Let's make an angle on this hill.
33. We don't have 30. He flipped the pages, y'all.
Come on.
I mean, what? We don't have it.
This isn't Sesame Street.
Well, where is it?
Let's make an angle here, not 40, not 50.
Is 33 even a number?
45.
Is 33 even a number?
No, we're only 45.
29 has an angle.
1.
29 has an angle?
Yeah, it's 30 degrees.
Yeah, but that's the rocket one. I'll do this one.
So let's put 30 degrees.
30 degrees. Alright, so, doing the car problem. What are the forces acting on this car as it's rolling down the hill and it's skidding to a halt, so you hit the brakes? Wait. Well, we'll say rolling friction because, oh, wait a second, hold on, no. It's, when you hit the brakes and the wheels lock up and it's like skidding, it's actually sliding. That's why it rubs the rubber off of the tire and it leaves like black marks along the road. So when you see like skid marks on the road, that's actually the rubber from the tire. Okay, so it's kinetic friction. Normal. Anything else? That's pretty much it. Okay. So we're going to draw our free body diagram. Obviously now again with our axes tilted. Where's the normal force? Perpendicular to the surface. Kinetic friction, which direction is that going?
Right.
To the right. And I'm going to draw that really large because this thing is slowing down. And then we've got the weight. Now what you could do if you wanted to was draw the weight pointing straight down. Alright? But then as soon as you do that, you're going to erase it because we're going to resolve that weight into its components. Okay? We're going to draw part of the weight going along this and part of the weight going along the y-axis. And it's just going to be weight on the x-axis, it's sine 30 degrees on the x-axis, and along the y-axis, it's weight cosine 30 degrees. Wasn't that so much faster? This is an example, yet again, of hidden information that you will need to know just on problems, okay? The hidden information is this. On ramp problems, item number 1, tilt the axis. Or tilt both of them. tilt the axes. And the weight in the x direction is just the weight sine theta, whatever your angle is. And the weight in the y direction is weight times cosine theta, where theta is between your ramp and the horizontal. If all of a sudden they give you this angle up here, okay, then everything switches and it's the cosines for the sines and the sines for the cosines. But if they give you this angle up here, I would just draw a little triangle and subtract it from 90 to figure out what that angle is here, because that's our formulas there are based on theta is the angle between the horizontal and the ramp. That's the other really big idea. If we get this down now, then it'll save us some time. So we talked about that and the Newton's third law. Okay. See you tomorrow. Or not.
Oh, that's it.